I will now take the opportunity to welcome our presenter. The San Diego chapter of Papers We Love is pleased to have Erik Aker from Qualcomm here to present. He's going to present on a 1992 paper by Philip Wadler entitled Monads for Functional Programming. We'd have a warm welcome for Erik, please.
Thanks, Marvin. So Marvin mentioned title, Monads for Functional Programming. Philip Wadler is one of the co-creators of the Haskell programming language. And of course, the paper does have Haskell in it. There's a lot of co-creators to Haskell. One of the other ones I'll probably mention is Simon Peyton-Jones. Haskell, the first Haskell meeting was 1987, and this paper came out in 1992 and became pretty influential. I think it's influential and famous not only within the world of Haskell, but within the world of functional programming. So I did implement all the code from the first 3 sections and the 5th section in Haskell. If you'd like to see that, this is my GitHub. I'm under EREWK. And there's a repo called talks. And inside there's a directory called Monads for FP talk. I'll have that at the end if you want to see it. I think there's kind of 2 different ways to talk about this paper, depending on the audience you're going to talk about it for. When I talk to people about Haskell at work, I'm usually talking to people who've never encountered it, maybe don't even know about it. So there's kind of like the audience, people who are familiar with it and familiar with functional programming, and people who aren't. And my guess, my theory is that people who aren't that familiar with it probably could use a little more of a section, like the first section could be filled out a little more. So I have a little bit of background that I wanted to kind of present, and I hope that it sets up these questions a little better. So these are questions I kind of use when I approach this paper. We want to know what problems Wadler's solving. And I think this is an important question a lot of people who are outside of the functional programming world will inevitably have. Like, why would you create a language where you need to do this to solve the problem that you have? Why would you create a language that has this problem to where you need the solution? And after you look at those questions, then you can really go, okay, what's he saying? How does this actually work as a solution for their problem? And this is another kind of question I think people go, well, okay, sure, you use this in Haskell, but do I need this in Java or Python or other languages? Is this useful for me outside of this niche world of pure functional programming languages? This is the approach I want to take. A little bit of history of functional programming, a little bit of history of Haskell, a little bit of lambda calculus. If you've never done lambda calculus, the interesting thing is lambda calculus has been called the assembly language for functional programming. Simon Peyton-Jones, in fact, wrote this book in 1987 called The Implementation of Functional Programming Languages. And it's just hundreds of pages of here's a particular feature we want to encode in our language, and here's how you turn that into the lambda calculus. And everything he adds on goes back to lambda calculus. And in fact, if you get sort of comfortable with lambda calculus, I think it actually makes Haskell much more, what's going on much more obvious. And then after that, we'll look at sections 1 through 3. We'll skip over section 4. And we'll look at section 5. The reason why I wanted to do that is if you end up looking at Haskell after this, section 5 talks about parsing. And that's actually a really common thing to encounter in the Haskell world. People are often writing parsers and using these parser combinator libraries. So this is the kind of thing you would encounter likely if you were going to do any Haskell in the future. So I think if you asked Philip Wadler, the author of this paper, if you said to him, what's a functional programming language? He would give you this answer. It's very simple. He would say it's a language based on lambda calculus. And I don't think he'd be interested in questions like, am I doing functional programming in JavaScript? Or if I have a functional programming library in Python, does that count? I don't think he's really interested in that stuff. He really seems to just sort of be interested in this idea that a functional programming language is simply a language that's based on lambda calculus. Here's a little bit of a chronology. 1958 Lisp. I might have that wrong. It's maybe 1956. That's generally considered to be the first functional programming language. In 1970, Scheme came along. That was meant to be a Lisp more closely modeled on lambda calculus. 1973, ML. And so in the 70s, there's this kind of percolating interest in this concept of functional programming. 78, there's this really interesting moment that's kind of a seminal moment where John Backus gives this Turing Award lecture called Can Programming Be Saved from the von Neumann Style? It's actually an interesting paper. Might be one worth reading here. And he makes this argument that by this point in time, 1978, he's sort of saying programming has gone down this cul-de-sac. We're sort of stuck by our mode of thinking about we have state and we have counters and we're just updating state. Right? And so he's saying we're actually missing this whole other radical and interesting avenue of potential for solving our problems, and that's functional programming. It's a direction that we should explore. It would be more, it'll link our work more to a foundation in mathematics and logic. And after that, maybe not necessarily causally related, but after that in the 80s, you have this like explosion in the programming language research community, interest in functional programming. And what would happen at that time is all of these language researchers, in order to do their language research, they would first create a language. They would create a functional programming language, typically a lazy, pure functional programming language. And so you had so many of these. Simon Peyton-Jones calls this the Tower of Babel period. Finally, in 1987, they had their first Haskell meeting. And their goal was, first and foremost, they were like, let's stop all making languages. Let's just make one, and then we'll do our research in that language. So their primary goal is to have a research programming language for programming language researchers to use, people doing this functional programming research. They wanted it to be based on lambda calculus, but typed lambda calculus. And they wanted it to be lazy. And one result of laziness is purity. Now, laziness means that an expression is going to be evaluated only when it's determined that it's going to be needed. So it's possible that something you may have encode some computation, it never actually gets evaluated. And there's this interesting thing that sort of results out of that, where the order in which stuff gets evaluated is no longer predictable, because you're sort of giving it up. You're sort of saying, here you go, compiler or whatever, or interpreter, evaluate this expression when you need it, but don't evaluate it before that. Let it just hang out unevaluated. And so purity was not their intention, purity meaning no side effects, but it happened as a result of laziness. And there's this interesting quote in this paper, History of Haskell by Simon Peyton-Jones. He says, an immediate consequence of laziness, evaluation order is demand-driven. So it becomes more or less impossible to perform input, output, other side effects as a result of a function call. You can't tell. Like if I say I need some input from a user and I'm going to then do something with that, you don't know when that input's going to be taken. You can't predict beforehand when that expression will be evaluated. And so early versions of Haskell, they would write these wrappers in C. It would compile down to C. But this meant that they couldn't do things like print to the screen or take input from users. Couldn't read files, couldn't write files. If you're doing it today, you can call out to the internet. And they had various solutions for this. And Wadler came up with this solution of the monad, and that became the solution for doing these side effecty things. Now this is a quote that shows up in the paper. Wadler says, pure languages such as Miranda and Haskell are lambda calculus, pure and simple. And he's of course using this word pure in a kind of playful way, I think. So he's saying Haskell really is just lambda calculus. And if you want to understand Haskell, one way to do that is to understand lambda calculus. So there are different ways to encode functions in lambda calculus. Lambda calculus is just a way of it was invented by Alonzo Church. And he wrote his famous paper same year that Alan Turing's Entscheidungsproblem paper came out. And Alan Church famously said, "I've come up with this way for doing logic. It may have other uses." He didn't think about it as a form of computation. Everything I know about lambda calculus I learned from this book. If you're curious about it, this is a fun book to read. It's got exercises in it. It's called Functional Programming Through Lambda Calculus by Greg Michelson. And all the examples come from this book. So this is, there are different ways to encode things in lambda calculus. This is a common way. This is a function expression. It's like what we would think of as a defined function. Left of the period is this, this is a definition. The lambda says I'm defining. This is the bound variable here. To the right of the period is the body. There's no keywords. There's nothing fancy. It's all functions. And this is actually the identity function. What this says is there's a bound variable x, and if you pass that to this function, what you will get back is what you passed in, that x. Doesn't matter what you pass it, function, anything else. There are other functions that are famous. This is called the self-application function. Notice to apply an argument in lambda calculus, you don't actually use parentheses. The parentheses here are just to disambiguate the body on the right side of the period from the definition on the left. And this says I have a bound variable s. If you give me an s, I will apply s to itself. Now, when you actually try to work with these things, they end up looking like equations like this. So we can do something like this. We can take the identity function, and we can pass the self-application function as an argument. And what happens is self-application function as the argument gets everywhere you see the bound variable x in the body is replaced by the argument. And we drop everything, the period and everything to the left, and we end up with simply what we started with, because it's the identity function. This process is called beta reduction. So when you are working with these equations, you're doing beta reductions and you're doing substitutions. When you can't reduce an equation anymore, it's said to be in normal form. You could do the opposite. You could take the self-application function, this is just another example, and you could apply as an argument the identity function to it, and here our bound variable s in the body will be replaced by this argument everywhere that s appears. So we drop the period and everything to the left. We end up with two of these, s and s, in this case, identity, identity. These parentheses are not necessary. Probably shouldn't have had it in there. This can be reduced again because we have a function and an argument. And so again, we take the bound variable x and we replace it with its argument everywhere in the body that it appears. And so that's your final normal form.
This may be a silly question, but how do you define a bound variable?
So bound variable is a variable that appears in the definition. Every lambda calculus function takes a single argument. They build it up, and they have strategies to build it up so that they sort of take more than one, but they're really just taking one. Right. The two terms you'll see, and this shows up in the paper, which is why I wanted to draw it out, are bound and free. So Wadler actually says, one of the things he says in the paper is he says functional programming languages are easier to reason about. And that may sound like a controversial statement. To him, it's like a completely non-controversial statement because he says the value of an expression depends only on its free variables. So what he's saying is this free would have come from some other function further up the chain and been bound already. This is waiting to be bound, and so we call it bound. Let me finish that thought. Marvin, question.
I looked this up, the free versus bound, on the way in anticipation of this. So say that you had actually a sigma notation, and you were doing a sum from k equals 1 to k equals 10 of n. K is a bound variable, and the reason that's easy to reason about is because you know all the possible values for that k. It's going to be 1, then 2, then 3, up to 12. The free variable is n. You actually don't know what the value of that is until it's provided, and that's why he says here the value of an expression depends only on its free variables. The value of that summation is going to depend only on the value of n, not on the value of k, because k is already known. Is that you're sort of looking skeptical over there?
I wouldn't call myself an expert, but there's something about that I think that kind of jives with how I would understand it. A lot of times in lambda calculus, they use the word. So if you imagine that this equation was bigger, that at one point there was a definition where the word free was a bound variable, it was on the left side of a period, and then we did some application, and we ended up so that it ended up looking like this. We wiped it away, but it's waiting for this bound variable to be introduced. That tends to be how Greg Michelson uses it. But let me kind of maybe go back to this thing, because Wadler, when he's talking about lambda calculus, he's talking about free and bound variables. What he's saying is there's no magic, right? If you want to know the value of an expression, there's no global state. There's nothing outside of the equation that you can call out to. There's no, like, this function can't call some other random function that isn't named explicitly here, and it cannot deal with any arguments that are not explicitly passed to it. And that's actually really how Haskell works as well. Maybe seeing a closure makes more sense. So like this is a common combinator, select first or select left, where you have two arguments. This is a function with two, well, it's a function that takes an argument and returns a function that takes an argument, which then returns the first argument that was ever given to it. This is a similar one. It takes a function and an argument and applies the argument as an argument to the function. And then this is a little bit same sort of idea, but even another level of abstraction, where everything takes one argument. So you've got first, second, and a function. First, we apply first as an argument to the function, and then we apply second as an argument to the result of that. So when you're dealing with lambda calculus, you're often dealing with these types of equations, and it gets almost easier to do it on
This
pen.
is referred to as currying, is it not?
Yeah, maybe. That's a tough one, actually. I don't know. In Haskell, they call it currying, but I don't think in this case it's called curry. Well, maybe it is. Actually, you could be right. So this is Haskell now. This is a Haskell function. This is a type definition for Haskell, and this is a function definition. This is typically how Haskell's written. You'll see a function with the type definition above it, and then no no types defined. Sometimes, rarely, if you need to help out the compiler. It has Hindley-Milner type inference, so you don't actually need this, but in most cases people provide it anyway. Now this is a totally kind of normal Haskell function. It looks like it takes 2 arguments, but it is curried. It takes an argument, and these parentheses are not necessary. I just included them so it's more obvious what's happening. It takes an integer and returns a function arrow here, returns a function that takes an integer which then returns a function. So it's really similar to what we saw above, where you take an argument and then you return a function that takes an argument which then returns a value. And actually Haskell gets compiled into an intermediate language called Core before eventually making it into like machine code. Core takes this and makes it into this. It looks just like lambda calculus. It says, okay, you want that? Well, here's what you get. You get this is the version of a lambda in Haskell. It's just a slash to represent it. I take an x, I return a function that takes a y, which returns x plus y. That type of stuff happens a lot, I think, in this paper. All right, so a little bit of background that I hope is useful or helpful for kind of understanding more the equations that Wadler's constructing in the paper. So he says, okay, we're going to use monads to integrate impure effects into pure functional languages. Purity, again, is one of the things we're kind of overcoming here, where we can't have side effects. It comes out of this theory in mathematics called category theory. I had never heard of that before being introduced to Haskell, but I've heard it described as the mathematics of mathematics. It's this kind of higher level abstraction meant to kind of unite the different areas of mathematics under common constructs and abstractions and terminology. He starts in section 2 with this evaluator for arithmetic terms. This is Haskell. In Haskell, you can write these algebraic data types. These are also called sum types. This is a type that he's defining, term. And he's saying a term can be either con, which is a constructor, but it probably means constant. It's some kind of integer. We're going to call it a con int. Or it's the division of 2 terms. And so one of the things that's, when you are first being introduced, I think, to Haskell, this can be a little funky, is this is actually a recursive definition. So you can build up these arbitrary kind of trees of these, as you see down here. So if you ignore the eval, I've got a term. This is a term, and it's defined as a div with a con 1 and a con 0. And so that's a term that ends up actually throwing a runtime error because when we evaluate it, it's divided by 0. So he has this type term, and he says, I want to evaluate these down. I'm going to create a kind of toy evaluator to turn these into integers, as if we're going to evaluate these as arithmetic expressions. So with an algebraic data type like this in Haskell, you can do pattern matching. This happens a lot in Rust also. You've got your match. And so he says, okay, if we have a con A, we want to get to an integer. We know we have one here. That A is going to be our int. We'll just return that. If we have a div t and u, those are terms, and we need to turn those into ints. So we'll just recurse down. What we'll do is we'll evaluate the left side. We'll evaluate the right side, the t and the u. And then whatever those results are, we'll divide the left by the right. How's that so far? Question, Marvin? Sure.
Is it cheating for it to throw an exception there? Because I don't see anything about that.
This is a real runtime error. I ran that in the GHCI, which is GHC is the common Haskell compiler. I ran it in the REPL and got it to throw a runtime error and just copied and pasted it in.
So just checking, is that somehow impure though? I mean, it shouldn't be able to tell me if it's it shouldn't be able to output anything.
That's a fair point.
Okay.
Well,
Okay.
I suppose in this case it is Haskell runtime gave you this error, but you cannot cache it. And the cache of the paper is how do you get that exception to your program instead of Haskell just crashing on you.
that seems like a fair response. So Wadler says, okay, we've got this toy evaluator for arithmetic expressions. Let's say we have some things we want to do with it. Let's say we want to catch. We want to watch out for maybe divide by zeros, and we want to return to the caller, hey, this threw an error, or you try to divide by 0. Or maybe we want to count how many operations. He calls this, maybe we have some state thing where every time we run this computation, we also have some other state we're going to manage or keep track of. That's a kind of side effect-y sounding thing. Or maybe we want to debug them. Maybe we create this really long expression. Somewhere in there is a 0, but it's not obvious, just looking at it. And so we need to be able to print out a term, or what we need to print out our evaluation before we actually evaluate it. So he gives these 3 motivating examples, and then he proceeds to introduce new types to represent these examples. These are all going to become kind of folded together under this concept we're talking about. So he gives them all the same name. Now, if you were going to write like a Haskell module, you wouldn't be able to write a module that all had, a type M, so later on I'll rename them. But he says, so let's look at exceptions. For exceptions, we can create a type. We'll just call it M. He calls it M because it's going to represent the monad. It takes a type, whatever you want, because this represents a computation, whatever computation you want, that may fail. And possibly confusingly, these are not keywords. They're names he gives to his constructors. He can call them whatever he wants. He calls the exception one raise, and it's going to return a string. And he calls the success one return. And he says, okay, A in this case is a computation you want to run, and we're going to do some additional computation where we're going to check, and if it's bad, we'll return to you raise exception, and if it's good, we'll return to you a return A value. And he says, well, in state's case, let's actually make that a function. So you've got a computation A you want to run, and I'm going to build another computation that runs every time you want to produce A. You're going to have to run this other computation. And in this case, he specializes state as an int. He says, we'll just count how many computations we run. And so we have a function from a starting, maybe a 0. We run it once, and we get to 1. So whatever your result value, that'll end up here, and we'll have maybe added 1 to it. And for the output part, he just pairs it up. He says, okay, this is computation you care about. We'll build up a giant string to keep track of the computation that we end up with. So I'm not going to actually do all of them, but here's the function that he ends up writing for handling exceptions. He says, okay, so I've got this exception type. It's called M. That's the type. It takes another type A. When you want to actually use it, you're going to have to tell the compiler, well, you don't always have to. But in his case, he's going to say, okay, we have a computation that we want to return an int, but we are aware of the fact that it might raise an exception along the way. So how do we evaluate this now? Well, we're still going to pattern match. If we have a con A, that's a success. So we're going to return this constructor. We're wrapping it in this data type, and that, in this case, success is return A. If it's a div tu, well, we still have to do what we did before. We still have to recursively evaluate the left-hand side, evaluate the right-hand side. So we're still going to evaluate the t. But in this case, when we evaluate it, we need to know if it failed. If it failed, the evaluation of the t will end up giving us back a raise e, and we can't continue. So we just return that. If it succeeded, the evaluation will give us a return A. Okay, so we've got a successful left-hand side. Now let's do the right. Same thing. Did it fail? If it failed, we give up. We give you that back. If it succeeded, now we've got a B. So we know we've got 2 integers, an A and a B. What we need to do now is check, is the B 0 or not? That's what he does. If it's 0, we're now going to throw another exception. Well, throw is the wrong term here. We're going to return to you this value, raise E, raise exception, raise string. If not, we're going to return AB. This is actually not the right Haskell term here. I probably should have stuck with that. Anyway, so again, evaluate the left, evaluate the right. If we have errors at any point, we'll return those. And we're still returning an M int because an M int is either a raise exception or a return int. If we get a successful A, a successful B, and it's not 0, then we'll give you A divided by B, and that should give you an integer. He then does state and the execution trace, and he says, and I didn't draw them out, but we'll do state later on. He says there's a pattern here, and the pattern is, these are all what he describes as monads. So this is a quote from the paper. It's a little long. He says, the original evaluator had this type. It took a term, and it turned it into an int. And in all the variations I wrote, it took a term and it turned it into an M int. And he says, so actually what we're going to do is we're interested in functions. Instead of functions from A to B, we're going to replace those by a function from type A to MB. And so here's how to read this, he says. This is a function that accepts an argument of type A, and it returns the result of type B with a possible additional effect captured by M. So this usually gets to this question. And this is a question that everybody who ever kind of comes to Haskell, I think, ends up asking. It can lead you down these rabbit holes. You can sort of find yourself in these paradigms of thought that make it difficult to really feel comfortable with what you're looking at. Personally made all the same mistakes I see people making all the time when they say, what is this? And so I'll try to maybe show you some of those landmines. But this is the actual definition. It's a data type describing a strategy to produce another data type. And this is maybe complicated, maybe not the right phrasing, but you want to run a computation, and we're going to have another one that goes along with it, an additional computation. There are two operations that it must actually implement, and it must adhere to three laws, but the Haskell compiler won't actually enforce the laws. So there is this phenomenon of unlawful instances, where people will kind of point out, oh, that's an unlawful instance. Now, this is the kind of big pitfall that people fall into. So a monad, people often, they reach for these metaphors that will unite all implementations of this. Right? So they'll say, well, a monad is a wrapper. It's a thing that wraps other things. Or they'll say, oh, it's an action. You hear that a lot with I/O. If I want to get a string from a user, I'm going to run an I/O action to get it. So you'll think, oh, well, all monads then are actions. Or it's a context. Maybe you could think of like the side effect raising as a type of context. There's a computation, but the context is, oh, there might be a side effect. It might be an exception. But you could also call that a side effect. I want to run this, and I want to run this on the side. Strategy is a term I find to be not too bad. The thing, though, is if you use these terms and you assume that this metaphor will give you access to understand or have intuition for all monads, that's going to lead you to a dead end. I know because I've made that mistake, and I've seen a lot of people make that mistake. The only way to understand a monad is to know that it is a data type in addition to another data type. There are two operations and three laws. The reason why we reduce it down to this is that you can implement the two operations for anything. There's an infinite possibility of ways in which you could define things as monads and say, yes, I'm defining this data type, and it adheres to the behavior of the monad, and it passes the laws. Bam, you got a monad. Is it a wrapper or a side effect or a strategy? It doesn't have to be. It just has to do these things. So that's the caution I would have there. Okay, so this is what it looks like in Haskell. Wadler calls this is a function, not a keyword. There's a lot of whinging about this, and it's sort of a painful part of the language. This is a function named return. It makes it even more confusing that you often see this at the end of monadic functions. People think, oh, return, but I don't use it in every case. It's not return from any other language on the planet. Wadler calls this unit. And this function, which he has as a star, is written like this in Haskell, and it's called bind. And he uses the word bind for it. And so a monad is a thing, your data type, which implements these two operations. You have to implement this function return, which means if you take in your function for your monad, it takes in an A, and it returns back an MA. So your monad can't be a bare thing like a string or an int. It has to be a thing in addition to a thing. It has to be able to take an A and give back your monad A. And in addition, you have to implement this function bind. And this is really key to understanding all the stuff he does later on, which means if you have a monadic value A, and you have a function from a pure A to a monadic value B, so you have a pure function that takes an A and turns it into a B with an additional effect captured by M, then what bind will do is it will take this MA, take the A, pass it to this function, and give you the result. So you have to implement that for your monad. So now here's his exception in, this is how you would implement it in Haskell. So this is compilable Haskell. I renamed it to accept M just because otherwise I have MA everywhere. But we can think of it as the exception monad or except monad. And in Haskell, you would actually define it as an instance. This is like in Rust, you know, where you're implementing interfaces for structs. Maybe I didn't have that right, but so here's our class except M. And if we take an A, we need to be able to return an except M A. And the way to do that is to return this constructor, return A. Right? So if I call return on a thing within the context of the except M monad, what I'm going to get back is this constructor. If I'm binding a value, it means I have an except MA value here on the left. And again, I've got a function from A to except MB on the right. This is an infix operator. So you can think of this as a function that takes 2 arguments, but you can write it infix. So what bind needs to do, it needs to take the A out of the left-hand side, and it needs to pass it to this function that wants a pure value but might raise an exception along the way. And so what it has to do is it has to evaluate that left-hand side. Is the M a raise E? If so, can't do anything. Got to return that. Is it a return A? Okay, cool. Well, K is this function. K wants an A. Well, there you go. That's the answer. How's that so far? Should I keep going? Pause on that one. So here's what that means. What it means for that specific one, right? Not what it means for all monads, what the except M monad means. It says we have the result from some computation that may have raised an error. And what we want to do is we want to take that result and we want to pass it to a new function that might raise an error. And we need to sort of string the value along from this previous possibly exception raising function to this new computation, to this new function which might raise an exception. Oops. So you can actually take his generic evaluator, his first evaluator, and you can rework it for any monad. This doesn't quite achieve what he wants, but it's possible to do this. You can call the generic monad instance. If you say, hey, I'm going to give you whatever monad you want, you got to tell me when you want to actually run this. But I'll give you a term and give it back to you in the monad you want. I'll give you an integer. And here's how I do that. I just call return because I know your monad must implement it. And I'll call eval, again, recursively. I'll bind that to a function that takes a pure A, and then I'll eval u. Notice how lambda calculus-ish it looks. Eval u would be bound to a function that takes a B, which calls return, and returns A divided by B. So that would work for any monad, but it's not gonna catch the divide by 0 problem. Here's an actual evaluator for except M. It's very similar to that. This is all repeated. Eval alone that we just saw won't properly handle divide by 0. So here's what we do instead. We eval the left, we eval the right. We check if the right is 0. And if so, then we'll return. He actually, I don't have it here, but he defines a function called raise, which just returns raise exception. That you don't really need that. You could just do his raise. Anyway. If B is 0, we'll return raise. Otherwise, we call return on A divided by B. So it's still specialized. You know, it's not like you can have one function that then works for everything. But it's simpler because this guy is handling a lot of the plumbing. It's saying, oh, did the previous exception raise? Well, that's all you got. We need to return an except M int, and it raised, and I'm going to just return that. I'm not even going to do the rest of this. Same with this bind down here. It'll do that for you. It'll look and see if the previous exception raised and just return that. Otherwise, it won't even call this function, right? So he has this line in there where he says, what's happening is we're going to perform computation M. We bind A to the resulting value, and then we perform computation N. And implicit in what he's saying is they're now using monads and bind to actually handle ordering. And so now you can sort of determine that the side effects are happening at the right time. Also have state. So he defines state in this way. A little tricky if you're doing this with like current Haskell, but it'll work for this purpose. State M is a function from state to A of state. The idea is that the state changes. Here's how he implements it. This one looks really tricky, and I've read this paper probably, I don't think it's an exaggeration to say I've read it like a dozen times. And probably every time I come back to it, I look at this and I go, is that right? Does that make sense? Okay, so a state MA, this one gets tricky because you always have to look at this. State MA is a function. If you give me a state MA, you're giving me a function from state to A of state, always. So if you're working within the state M monad, you're giving people back functions that are waiting for states. So return X just constructs a brand new function from state to X of state. Actually won't change anything, right? It just says give me a state, I will give you back the same state. Bind has a state function on the left-hand side, right? That's the M, the MA, the state MA. On the right, it's got a function K that wants an A and will return a state MB. What is state MB? It's a function waiting for a state, and it will give you a B of state. So K actually is a function from an A to a function state to a B of state. K is actually a function that, if you were going to fully evaluate it, will take 2 arguments before it finally gives you a result. Question, Marvin?
Just a quick clarifying question. You keep referring to that M as an MA. But I'm confused. Why is that an M and MA? Or
Sorry, yeah, that's my fault. So before, when he's defining his data types as capital MA, that's that monadic value, right? That's the type. So when I'm saying MA, in my mind, what I'm saying to you is the type of this thing.
Okay.
And in this case, the type of it is state MA. So what I'm trying to say is, I'm trying to link. So this, when you do enough Haskell, you get to a point where the type signatures are almost more important than the implementation, where you can build the function purely by looking at the type signature. You look at it long enough and you go, oh yeah, it's like the code almost matters less. And people told me that when I started, and I didn't believe them. And I was bad at reading these, and then the more comfortable I got with these, the more I relied on them. And I think what's happening is I just automatically am going back to it. So M is this. There's some A wrapped up in M, right? And what M is, a state MA, is M is a function from state to A of state. So how do we get the pure A out? Well, the way we do it is we actually have to run M. It's a function. And so what we need to do to run M is we need a state. So this bind, this definition, starts off by saying, okay, if you give me a state, I will start this computation. I will take that state, I'll run M with it, which will give me an A and a new state. I can then take K, which wants a pure A. K is going to return a state to a B of state, but we're sort of left hanging. We're not done yet. I need to give it this state to return a final value. And so actually you go from this state MA, which is a state to A state, and you kind of build a function around that function using bind, which says, well, give me another state, I'll start that first computation, I'll run the next one, and you'll get your end value. But what you end up with ultimately is a function from state to B of state. That one's tricky. Question? Yeah, the type definition.
So is every instance of Monad going to have a bind termination to bind?
Yes. And they're always going to be MA, whatever the monad is, A to MB. That's the function that you're going to give bind. You have to give bind a function, and they're always going to return an MB. So what does state mean? State is a form of function composition. State says, you give me a state and I will start the engine, right? I'll run your first computation, I'll figure out how to take the value out of it, I'll run your next computation, and I'll give you the result of that. And so state is this kind of, it's function composition. And then finally, here's the evaluator for state M. He says, let's make a function called tick. And interestingly, if you look at this, this is the unit value in Haskell, which is like a void. It's a no value. It's a constructor with, this is the only occupant inside it. So tick is a function, is a function within the state monad, right? It's a function from state to nothing, but it just sort of ticks along the state. And so you can actually interweave. This is also in the same monad. So you can interweave this with your evaluations. And that's what he does. He says, okay, if you give me, we're going from term to state int now. If you give me a con A, I will just return your A, And you have to sort of imagine, again, a type signature, state MA. This is a function from state to A of state. In that case, where state's unchanged, if you give me a div TU, I need to do what we always do. I need to evaluate the left. I need to evaluate the right. We're going to use bind to link these things. And we're also going to insert yet one more computation, which is tick. And we're going to bind out the result of tick, which we don't care about. But what tick will do is it will take the state from these guys and it will add 1. And return will end up, because again we're dealing with bind, return will have that state and return A div B. So these are functions composed together, where state is carried along throughout. Okay, so he defines those things, and then he says, okay, section 3. Section 3 is sort of short. He says there are laws you have to follow. To legitimately call the thing that you have implemented a monad, it should adhere to these 3 laws. The 3 laws are left identity, right identity, and associativity. And the idea with the laws is that if you manage to create a monad instance that's not lawful, then its behavior is sort of less predictable. One way to think about that is we were sort of talking in the meetup conversation, and I said, oh yeah, you can think of integers, for example. Like if you're adding, if I were to say to you, oh, I have these integers, and when I add them, they're not associative, right? Like, like you can actually add them in a different, like if I add 1 and 4, and then I add the result to 5, you're going to get a different result, whereas if I add 1 to 4 plus 5, and your kind of immediate response is, that doesn't sound like integers. That's not addition, what you're doing, right? There's something wrong there. And that's kind of the same thing with monads. They have these laws to govern their behavior, but more to say they belong within the set of things called monads. If they adhere to the laws, then yes, they can be called a monad. So laws maybe sounds a little strong. So here's left identity. And the way in which these definitions often work is you really have to think of the type signature of bind and what return's giving you. So if I have a pure value A, and I want to turn it into a monadic value with return, I'm going to get my MA, whatever the monad is, right? Capital MA here. Bind is going to take an A out and pass it to a function A to MB, right? So if I have a return A and I bind that to a function K, well, this should be 3 lines there for equivalence. This is equivalent to just taking the A and passing it directly to the K. Again, K is a function from A to MB. If you first wrap your A in return and then you use bind to thread it to the K, it's as if you just gave it directly to the K. These are equivalent. Right identity is really similar. If you start with a monadic value on the left, that's a capital MA, whatever the monad is, you use bind to pull out the A and you give it to a function K, whatever that function is, A to MB, you'll get the MB. Well, here, return's not going to change the A to a B, but that's fine. You're still going from a pure value to a monadic value. So if you start with a monadic value, you use bind to pull the pure value out, and then you send it to return. This is the same thing you started with. This will not actually modify your initial value. And this is important because if you have a monad and you implement return in a way where something funny is happening, and this identity no longer holds, then when people are using it and they're calling return, the behavior they get might be unexpected. Associativity is the last law. It's the one that I struggle the most to describe, so I hope I do an okay job here. The idea with associativity is that ordering matters. He says it doesn't matter where the parentheses go. Ordering matters, but it doesn't matter how you nest the computations. So that example I gave of integers would kind of hold. I saw an example online where somebody said, it's like with list concatenation. This may satisfy you, but I struggle with it. The example was, if you have 3 lists, A, B, and C, and you concatenate A to B, and take the result of that and concatenate it to C, it's the same as if you're concatenating A to the result of concatenating A, B, and C. Now that doesn't mean that that other expression's happening first. The ordering happens at the same time, but that's the idea behind associativity. How'd I do? Is that terrible? It's okay. So the last section's parsers. I didn't want to do too deeply on parsers. A lot of that stuff is pretty interesting. First thing is, I use a new type. So a new type is a a way of kind of, it's like sort of like a type alias. The reason I did that, I didn't realize I copied this from that. The reason I did that is that making monads out of pure type aliases in Haskell is a little, well, anyway. You can kind of ignore this stuff. Imagine it's just type parser A equals state to, in this case, it's a list of A and states. So the parser monad looks just like the state monad, except instead of state to A of state, you get state to a list of A and state. And here's what's kind of funny about that. He says that there's 2 points he makes. He says, do lists have a monad implementation? Yes, they do. And he describes it as non-determinism, which we'll come back to in a second. He says, here's why we're going to do this for parsing. You may parse a value. Let's say you get a string. The string is 1, 2. And you want to parse that into an integer. Is it 1? Is it 2? Is it 12? Now, your probably initial reaction is to go, well, that's 12, obviously. But the way he builds the parsers up is he's saying these are all valid parsers. Well, maybe not the 2. But 1 and the rest, and 12 and the rest. Those are valid parsers. So you take one input and you get a number of different outputs. And that's the weird thing about the list monad. When people describe it as non-determinism, when I first heard that, I struggled for a long time with that. It's like, how can a list be non-deterministic? You know, well, the thing at index 0 is always going to be at index 0, right? Unless you start moving stuff around. But the idea is, again, if you go from an A to a monadic B, you start with a value A, you're turning it into a B, but it's within this monad. If the monad is list, you're going from an A to a list of Bs. And within the context of Haskell, if you know nothing about the A's, you can't make any assumptions about them. You can't compare them for equality. You can't. It's just a generic thing. You go to a list of results. The only way to interpret that is to say that there are many possible answers for your computation on A to result in a list of Bs. So that's why they call it non-determinism. There are many possible answers, each of which is equally valid. And so that's what's represented here. And he says, okay, now I can define, he defines all these interesting parsing functions. First one he starts off with is a parser for individual characters. In Haskell, a string is somewhat notoriously a linked list of UTF-16 code points. So you can actually treat it, yeah, it's pretty bad. You can actually treat a string as a list, just like this is list, you know, syntax. A string is a type alias for a list of characters. Anyway, so that's what he does. You know, he says if I want to parse a single character and I have an empty string, the only thing I can give you back is an empty string. If I have an initial element of the list and the rest of the list, A cons onto X's, you know, it may be, this may be empty, maybe a million, maybe 1, whatever. We're only parsing 1, so we'll just say, oh, cool, there's your 1, here's the rest. And that's how his parsers tend to work. We parse a thing, we give you the rest. He then defines his parser class, his parser type as an instance of monads. He says this is a monad. How is it a monad? Well, a parser, you know, if we are going to return within the parser, we're going to take an input X, and we're going to return it back unchanged. The return value, again, just sort of builds up the initial monadic computation. If we have a parser M on the left, and a function that goes from a pure value A to a parser B on the right, we need to do something very similar to state. He uses, this is list comprehension notation, which might be a little bit, tricky, but what's happening is we're first going to take, you know, so it's like the state. We take our initial, you can think of this as state, X. We're going to pass it to the first function M, which is a parser. That'll give us back a list of A's and Y's. You know, our parsed value A and the rest value Y. With those lists for every one of those AY's, we're going to pass to our K. And again, it's like state, so K will end up taking 2 arguments. It'll take its starting state, and it will take the state that you're progressing, right? It'll take your initial value, your pure value, and the state. So for every AY, we pass the A to K and the Y to the result, and we'll get a list of BZs. And so really, we're chaining these parsing computations. He says, unit corresponds to the empty parser, which consumes no input. Bind corresponds to the sequencing of 2 parsers, just like his state example earlier. It's like function composition. We're first going to do this. then we're going to do that. And so he says, here's his illustration. He says, I have my item, which parses a character. If I want to parse 2 characters, I have my item parser. I bind the result to a function that takes an A, which then runs item, and binds the result to a function that takes B, and then returns A paired with B. So this is a parser character, right, which is waiting for initial string to parse. It'll return the first 2 elements from that string. He then builds up all these interesting functions. He has this alternation function. This is 0, right, which fails on everything it gets. Whatever you give it, it will give you an empty string, meaning, sorry, give you an empty list, meaning no parse. So that's his identity function for parsing. He gives you this, let's do all the different parsers we can. If you give me a parser N and a parser M, and I want to run both of them, I have this operator. So you give me an X, well, first I'll run M, and it'll give me a list of results. Then I'll run N, and I'll just concatenate those list of results together. So you got 2 parsers, and I give you everything that you can get out of those 2 parsers. And then he builds this filter function. He says, like, maybe you got a parser M, and you want to know if the result of the parse fulfills a particular predicate. So we'll start with a value. We'll run the predicate. We'll start with our computation, and we'll bind that to a function that takes the resulting parse value, tests it with P, and if it's good, then it returns it. Return, again, the monadic function. Otherwise, it just gives you fail. We can then build, is this a letter, by parsing an item and then passing it to this is letter. We can do the same for digit, which will return in numeric value. We can check if you have a literal, like if you want to look for particular, like a semicolon or a question mark. You can create a function that does that by creating a predicate that tests. So that's his parsing. Went through that pretty fast because it's kind of dense. And so this is kind of the last thing I would say about the paper. Why? Yeah. So why is this interesting? For Haskell, he says integrate impure effects into pure functional programming languages, but none of the monads we've looked at are impure. None of them do anything where they're like reaching out into the ether and pulling out these values, from memory or from anything. I/O, really, when you're doing input-output, that's an impure monadic effect. But they allow side effects, so they introduce side effects in the language. One other thing is that when you're working with Haskell and you see a monadic value, you know there's this additional computation. It forces your awareness that there's a side effect. It doesn't break what they call referential transparency, where if you look at everywhere you see the definition of a function, you can replace it with its body, just like in the lambda calculus. Again, there's no kind of other bizarre things that are magically available to any function in Haskell. And just because you have a monad doesn't mean you have access to these other like invisible parameters and things. It all has to be threaded through. Out of the tar pit's a really interesting paper for talking about side effects. It's really long, 66 pages. I think it's worth reading. You might want to discuss it here, but let's talk about side effects and as a source of bugs, as a source of complexity. So this is the other question I kind of promised I would try to get to. What can other languages learn from monads? And one is awareness and isolation of side effects. Out of the tar pit talks about this a lot, that if you're aware of side effects and you kind of corral them, then you're more likely to sort of defeat the pernicious effects of not being aware they're happening. Another thing is that a lot of languages probably already are using monads. They're just not calling them monads. One thing that happens a lot, I write Python every day, is like, I'll call a function that maybe returns none. It's like an option or a maybe, right? Did it give me a none? Oh, okay, I'm returning none. It didn't. I need to take it and run another computation, which may itself return none. That's the monadic interface. This is maybe perhaps a definition of terminology. It may be called a maybe monad, but in Python there's no name for it because it didn't need to have one. We don't have a side effect problem in Python. I can call side effects willy-nilly. Any function can, launch nuclear weapons if it wants to. Elm has, I mentioned this, Elm has an and then. They have a monadic operator, but they don't call it a monad because they want to be beginner-friendly. They're afraid that it will turn people off. JavaScript, futures and callbacks, those may be monads, the way people are using them. The argument that comes up a lot is that if you use this term monad, you're actually linking what's happening here to scholarship in mathematics. And so if anybody comes over from mathematics, they have this whole legacy of research that they can call upon to understand what's happening here. And it's possible that you could sort of work together, that you sort of progress together. That's kind of the argument people make. Finally, this is the last thing. Here's a quote from Simon Peyton-Jones. It's kind of long. He says, whether a pure language with monadic effects is ultimately the best way to write programs is still an open question. But he calls it a radical and elegant attack on the challenge of programming. Kind of like that. Combination of power and beauty, he says. He says, in retrospect, the single biggest benefit is not laziness, but that laziness kept us pure and motivated a great deal of productive work on monads and encapsulated state. And this is like, the jury is out today on laziness. There's a language called PureScript. It's a pure functional programming language. It is strict. And I think Ictus might be strict. There's all these languages where people are really interested in creating pure functional programming languages, and they don't necessarily care about laziness. And these guys in the 80s, laziness is what they wanted. And it almost looks a little weird and quaint nowadays. But because of laziness, they had purity, which meant they had to kind of work through this problem, and they ended up introducing monads, which became a thing that became pretty influential. If you're curious, there's a lot of other stuff to read. Functional programming through lambda calculus. If you're curious how I/O is implemented in Haskell, there's a paper called Imperative Functional Programming. I/O is the weirdo monad. It's an interesting paper. The paper on history of Haskell is fun to read. It's not highly technical. It just talks, like all that history stuff, pretty much all comes from that paper. That's a longer paper, but I find it fun to read. And then this guy's a prolific Haskeller, Stephen Deal, and he has a pretty well-known resource called What I Wish I Knew When Learning Haskell. And in there, he has this one thing where he says, the eightfold paths, Satori path to monad enlightenment. And the first line is, there isn't one. Data type, 2 operations, 3 laws. Anyway, thanks.